Here are solutions to homework set number 6 for ECE 463-663 Modern Control. In this homework set, we look at finding feedback gains using pole placement, or Gura. The first problem is the cart and pendulum system. I want to stabilize this system and give it a step response that looks like this. I want 5% overshoot and a settling time of 5 seconds. Come up with a feedback control law that does it using this form. Full state feedback, kx times x, plus an input gain kr. Well, the first step is to translate the requirements into pole location. So 2% settling time of 5 seconds says the real part of the pole is at 0.8, minus 0.8. 5% overshoot tells you the angle of the pole. From the second order damping approximations, 5% overshoot gives you a damping ratio of 0.69, or an angle of 46 degrees, meaning if I want the closed loop dominant pole to be right here. Real part's 0.8, and the complex part is 0.83. So come up with feedback gains to put the poles there. Well, I can do that using Gura. I'm going to place the dominant pole at 0.8 plus minus j 0.8, and the other two don't really matter as long as they're not dominant. So I just stick them at minus 5, minus 6. To do that using Gura, or pole placement, input the system's A matrix, B matrix, C and D. Use pole placement to place the poles there, and that's my gain kx. So there's my feedback gain, and as a check, the eigenvalues of A minus B kx should be where I put them. And they are, so that looks good. Now find kr to make the DC gain 1. Next step, check the step response of the linear system. So here's the closed loop A matrix, A minus B kx. Here's the closed loop B matrix, B kr. C and D don't change. I'm looking at the position of the cart. I'll plot it for 8 seconds and check the overshoot. I want 5% overshoot. I actually got 5.7%. So I plot the overshoot. Here's the linear system. It's got this non-minimum phase, goes negative for a while. Kind of annoying, but that's how the system behaves. To check on the linear system, or the nonlinear system. Let's go over to MATLAB. So in MATLAB, and find my script. There it is. Make sure you've got the correct dynamics. So let's get this out of the way. Go under cart dynamics. This is the correct dynamics. Cart is 4 kilograms, ball is 1 kilogram, length is 1.3 meter. Under cart, change the feedback gains to what we calculated, kx and kr. Apply a step input. I'm going to go from plus 1 to minus 1. Actually, 0 to 1. And here's my control law. I'll then find the dynamics, integrate, plot, and here's what she looks like. Maybe. And let's do that again. So if I run this, here's the cart. I'm going 0 to 1, 5% overshoot. Go back to 0, 5% overshoot. Behaving pretty much like I expect. So that worked. We're able to control a cart and pendulum system. Next problem is a ball and beam system. Here, what I want, let's get that out of the way. Let's see, where are you? This is the response that I want. I want to take a ball and beam system, like this, apply torque on the beam to get the ball to roll to the right and wind up at plus 1. Get there in, whatever that was, 5 seconds with 5% overshoot. And then go back to 0. How do you do that? Well, again, it's about the same procedure that we had before. Come back here. There we are. First, I want to take the linear system. This is what we came up with in homework set number 4. Take the linear dynamics, your A matrix, B matrix. Using pole placement, place the poles at minus 0.8 plus minus j.8 and somewhere else. Again, it just shows minus 5, minus 6. Do that and you get feedback gains. Checking. Gains are correct. Find Kr to make the DC gain 1. For the linear system, plot the step response. And that would be the closed loop A matrix is A minus B Kx. Closed loop B matrix is B Kr. C and D. So linear system looks right. I've got my settling time, overshoot. Now let's try the nonlinear system. So again, for the nonlinear system, I apply the same feedback gains, Kx, Kr. Have my step input. This just goes from 0 to 1, back to 0. Feedback control law, U is Kr times ref minus Kx times x. Integrate, repeat, and she works. Now this is the actual acid test. You want it to work for the nonlinear system. If it doesn't, it could be that the two poles that don't really matter, the pole at minus 5, minus 6, you stuck them someplace where that doesn't really work. I want to keep the gain small. If it's too large, I get nonlinearities. Like if the beam angle goes past 90 degrees, the ball falls. If the gains are too large, like I put the poles I don't care about, like at minus 100, minus 200, gains will be too large. Play with the other two poles, try to get them so that these gains are small. And that's one of the challenges with pole placement. Where do you put the poles you don't care about? They do affect the response. By making the gains too large, the nonlinearities start to play a role. But this seemed to work. So that's problem 2. Problem 3 is take a double pendulum. Same problem. So what that should look like when you're done, let's go back to the simulation. Get me out of the way. I'll have the double pendulum system. Again, I want to go from, in this case, went from minus 1 to plus 1. And then go back to minus 1. Come up with the feedback control law to get this to work. In this case, these can swing fairly violently. How do I come up with a control law that doesn't do that? Gives me a nice, clean step response. Well, again, same procedure as before. Take the closed loop A and B matrix. Actually, take the dynamics of the system. Here's the system's A matrix and B matrix. A and B. Make sure it's controllable. It is. Place the poles where you want. In this case, I chose, for 10-second settling time, the real part's minus 0.4. Complex part is 0.42, gives you 5% overshoot. And the other poles, I don't really care where they go, just so they're not dominant. I just stuck them at minus 2, 3, 4, 5. Do that, and you get your feedback gains. There's Kx. Checking, the pole location is correct. Find Kr to make the DC gain 1. And then check the linear system. Here's the closed loop A matrix, closed loop B matrix, C and D, just looks at position. Plot them, everything looks good. I've got 5% overshoot-ish, 10-second settling time. Now try the nonlinear system. Use the same feedback gains that I just calculated in the nonlinear system. So here's your U, find the dynamics, integrate, plot. And hopefully she works. In this case it did. And you get this response. So that is homework set number 6 for modern control using pole placement. What's neat about pole placement is, like in this case, I've got 6 degrees of freedom, 6 energy states. Coming up with 6 feedback gains by hand is not easy. With pole placement, I just specify where I want the poles to be, and the 6 feedback gains, Kx, just drop out. Apply them, and ideally, The system should behave the way you expect, the poles being right where you put them. Homework set number 6.